Hello, you're welcome to this lesson. In this video, you are going to solve this question I have on the screen. The question says the spring in the toy gun has an unstretched length of 100 millimeters. It is composed and locked in the position shown. When the trigger is pulled, the spring unstretches 12.5 millimeters and the 20 grams ball moves along the barrel. Determine the speed of the ball when it leaves the gun. Assume the coefficient of friction between the ball and the barrel to be 0.2. So this is the question we have. So to solve this question, we are going to use the principle of work and energy conservation. Okay, so let's look at what you are going to do. So the principle says that the sum of work, the sum of work done by forces acting on a particle, okay, causing the particle to move from position 1 to position 2 should be equal to the change in kinetic energy of the particle. So this is the equation you are going to use. Okay, so now let's look at the term on the left hand side, which is the sum of work done by the forces acting on the particle. So the particle here is the ball in the spring gun. Okay, so that's the particle we are considering. So looking at the particle, okay, the force that will cause it to move will be the spring force. Okay, so for this reason, there's going to be work done by the spring force. So that's one of the works. And also because there is friction between the ball and the barrel, there's going to be work done due to friction. So you have to find both. You have to find the work done by the friction and then work done by the spring force, and then sum them up and then equate it to the change in kinetic energy. So let's look at how we are going to do that. Okay, so first of all, let's look at the work done by the spring by moving the ball from position 1 to position 2. Okay, so for that one, we are going to have, let me name it USP. Okay, that's work done by the spring. Let me write it again. Okay, so you have USP, work done by the spring. Okay, this should be equal to 1 over 2 multiplying K into bracket S1 squared minus S2 squared. Okay, this is the formula we are going to use to find the work done by the spring, where K is equal to the spring constant. And then S is equal to the displacement of the spring. Displacement of the spring. Okay, so now the spring constant is given to be 2 kilonewton per meter. Okay, so you have that one there. So you're going to have the K to be equal to 2000 Newton per meter. Okay, and then for the S, you're going to have two displacements, which is the initial displacement and then the final displacement, which is S1 and then S2. Okay, so now let's look at something here. So initially, we've been told that the unstretched length of the spring is 100 millimeters. Okay, so which means that the original length of the spring when no force is acting on it, or when it hasn't been compressed, is 100 millimeters. Okay, so let's take it to be this red line that I've drawn here. So this is the original length. Okay, so let's look at what I'll do. So this is the 100 millimeters. Okay, which is the unstretched length of the spring. And now it has been compressed to the position shown, which is the 50 millimeters. Okay, so now the new length that we have will be this length. Let me do this. Okay, which is the 50 millimeters. 50 millimeters. Okay, so let me write 50 millimeters here. Okay, and then it was unstretched by 12.5 millimeters. Okay, so look at what I'll do again. So I'm going to have, after we get into the 50 millimeters, okay, which is this point that I have here, it was unstretched again by 12.5 millimeters. So we will continue a little bit. Okay, we continue a little bit. So that distance will be the 12.5. Okay, so now we are going to have the 50 plus the 12.5, right? We already know that from here to here becomes the 50, and then we are going to have the 12.5 here also. Okay, so this is what you have now. So you have the 50 and then you have the 12.5 millimeters here. Okay, so now what you have to measure is the displacement. Okay, so let's look at how you're going to measure the displacement. So this distance now becomes S1. Okay, and then this small distance here to becomes S2. So this is S2, then this is what? S1. So let's look at how you're going to find S1 and S2. So S1 will be equal to the 100 millimeters minus the 50 millimeters, which will give us 50 millimeters. And then you have to change this to meters. So you have to multiply by 0.001. So you're going to have 0.05 meters. And then S2 will be equal to 100 minus 50 plus 12.5. Okay, so let's do this and see what you're going to get. 100 minus 50 plus 12.5. So when you do this, you are going to get 37.5 millimeters. Okay, so let's change this to meters. So that will be 37.5 times 0.001. That gives us a value of 0.0375 meters. So now we know S1 and S2, and then we know our K. Okay, so let's substitute them into this formula that we have here, and then find the work done by the spring force. Okay, so you are going to have the work done by the spring force to be equal to 1 over 2, okay, 1 over 2 multiplying K, which is 2000 Newton meter, okay, times S1 squared minus S2 squared. So you are going to have S1 squared is 0.05 squared minus 0.0375 squared, and then square bracket. So now let's simplify this and see what we will get. Okay, so the half of the 2000 will give us 1000. Okay, so let me write this here, 1000. Okay, and then I was supposed to bring the units there, that's the meters for the displacement, but there's no space, so I omitted it. So let's take note of that. So I'm going to have 100 Newton per meter, okay, and then let's multiply by the terms in the bracket. So I have 0.05 squared minus 0.0375 squared. Okay, so that gave me 1.09375. So let's make it 1.094, okay, times 10 to the power minus 3 meters squared. Okay, so this meter will cancel out the squared here. So you're going to have work done by the spring to be equal to 1000 times 1.094 times 10 to the power minus 3. Then you're going to have this to be 1.094 Newton meter. Okay, so this will be the work done by the spring force. So now, since there is friction, there's going to be work done due to friction. So you have to find that one also. And frictional force will be equal to the coefficient of friction times the normal force. Okay, and then when we look at the ball, let's say I have the ball here, and then the spring force is acting in this direction. Okay, and then we have the weight force to be pointing downwards, and then this is the weight force, and then this is the force of the spring. Okay, and then this will be the normal force. Normal force should be N. This will be the normal force, and then we have frictional force in this direction, which is the Fr. Okay, and then that will be equal to the coefficient of friction times the normal force. And since the normal force will be balancing the weight, we're going to have the normal force N to be equal to mass times acceleration due to gravity. So therefore, the frictional force will be equal to coefficient of friction times the mass of the ball times acceleration due to gravity. So let's look at that. So you're going to have 0.2 times the mass. The mass was given in grams, so you will multiply it by 10 exponent minus 3 so that you get it in kilograms. So you are going to have 20 times 10 to the power minus 3. Then that will give us the mass to be 0.02 kilograms, okay, times 9.81. So let's simplify this and see what you are going to get. So I'm going to have 0.2 times 0.02, okay, times 9.81. So this will give us a value of 0.03924. Okay, so you have 0.03924 Newton. Okay, so this is what you get for the frictional force. Okay, so now let's look at what you need to do again. So now you need to calculate the work done by the friction. Okay, so let's look at that. So at first, the ball was at this position here, okay, as shown, and then it's unstretched by 12.5 meters. Okay, it's unstretched by 12.5 meters. So which means that it will move a little distance. Let's say this distance here. Let me indicate that with a different color. So let's say it moved some small distance here, okay, which is the 12.5. Okay, so what will happen is that because there is friction between the ball and the barrel, okay, when the ball is moving from the red point here to this point, there's going to be friction throughout, because within that range there will be friction between the ball and then the barrel of the gun. So frictional force is going to act so far as the ball moves through the barrel. Okay, and then looking at the length of the barrel, which is 200 millimeters, the ball was initially placed at the 50 millimeters. Okay, so this is the actual distance left for the ball to travel before leaving the barrel. So as soon as the ball is released, it will travel a distance of 150 millimeters. And so far as the ball starts moving from that point, there's going to be frictional force throughout. Okay, there's going to be frictional force throughout the 150 millimeters. So all this means is that frictional force will start acting from the point the ball started moving till it leaves the gun. So the frictional force will act through a distance of what, 150 millimeters. So to find the work done by the frictional force, you have to multiply the frictional force by the total distance traveled by the ball before leaving the barrel. So for this reason, work done by the frictional force, which I'll name U, FR. This should be equal to 0.03924 times the 150 millimeters, but we are changing it into meters. So we are going to have 150 times 10 to the power minus 3 or times 0.001, which will give us 0.15. So let's simplify this and see what we get. So 0.03924 times 0.15, that will give us a value of 5.886 times 10 to the power minus 3 Newton meter. So this is the work done due to friction. So we have this here. So now we'll be able to find work done by the spring force and then work done by the frictional force. So one thing you have to know is that since the ball is trying to move in this direction, okay, when the spring is released, the ball will try to move in this direction, but the frictional force will try to slow it down by acting in this direction. So for that reason, we will say the frictional force is acting in an opposite direction to the motion of the ball. So we will have to negate the frictional force in our computation. So let's take note of that. So now let's look at how you are going to calculate for the change in kinetic energy. So initially the ball was at rest, so that makes the initial kinetic energy 0. So T1 will be 0. Okay, and then what you have to do now is to find T2. So for T2, which will be half mv2 squared. Okay, we know the mass of the ball to be 0.02 kilogram. So you are going to have T2 to be equal to 1 over 2 times 0.02 v2 squared. Okay, this is what you are going to have. So now let's do the substitution and see what you are going to have. Okay, so before I go ahead, please make sure you like and subscribe to this channel. Okay, so you like the video and then you also subscribe so that you can get updates. So now let's continue. So we know work done by the spring force and then work done by frictional force. So now let's substitute them into the main formula. So you're going to have 1.094, okay, minus, because the frictional force is acting in an opposite direction, so you have to negate it. So minus 5.886 times 10 to the power minus 3, okay, 10 to the power minus 3 Newton meter. Okay, this should be equal to the final kinetic energy, okay, which will be 1 over 2 times the mass, which is 0.02 kilogram, okay, times the final velocity squared. So the only value we don't know is the v sub 2. So let's find it. So I'm going to compute all this together at once. Okay, so let's look at that. So we are going to have 1.094 minus 5.886 times 10 to the power minus 3. Then that will give me a value of 1.088 to be equal to half times 0.02. Okay, that gives me 0.01 v squared. So now I want to find v2. So we are going to have v2 to be equal to the square root of 1.088 divided by 0.01. So let's see what we get for v2. So the square root of 1.088 divided by 0.01. So that gives me a value of 10.43 meters per second. So this will be the value of the velocity, which is the final velocity of the ball before it leaves the gun. Okay, so guys, one thing you have to know is that you might not get the same answer that I got, which is the 10.43 meters per second. Okay, if you don't get that same answer, then because of how the rounding of numbers were done during the solution.